This is a third overtone crystal for 10 MHz. And I will look at the properties of this. I don't have any data. First, I want to know the unloaded Q. So I have connected the crystal to two very small capacitors with air dielectric. It's these two small pieces of copper, one from each side, and they couple to the wire from the crystal. And then I have a transformer and another capacitor to balance the capacitance between the two copper sheets. So I think this is what I can see now is the performance of the crystal itself with no capacitive load, almost. And this is what I see in the spectrum analyzer. And I want to look for the bandwidth. It says Q is 1.39 million. And of course the loss is very high because I have very small capacitors coupling to the crystal. So this should be the unloaded Q when there is no capacitive load on the crystal and no resistive load either. Now I have placed a 1 megohm resistor in parallel with the crystal, and I'm running the network analyzer a little faster because there is a frequency drift after I had the soldering iron in the neighborhood. But now the curve is still enough so I can look for the bandwidth and marker and marker, search and bandwidth. And now Q is 1,141,000. And I removed that resistor now. And the capacitance of it shifted the frequency. But I can still see the Q. 1.388 it tells me now. So 1.4 and 1.14 for 1 megohm. Now I have loaded the crystal with two small capacitors, 4.7 pF polystyrene. It seems the impedance is much lower, but I haven't lost Q. It's 1.45 million. Maybe it's even a little higher. With the very small capacitors, this is the schematic diagram, I observed 1.39 million on the Q, and with the 1 megohm resistor it dropped to 1.14. Now Q is R times the square root of C over L. If I assume that C hasn't changed, I find that the ratio is 0.82, and that leads to an impedance of 4.5 megohm. I tried to put coupling to input and output through 4.7 pF, and that degraded Q down to a little bit above 1 million with a loss of 14.5 dB. So I put 1 nanofarad to ground on each side to make the coupling to the source and sink of the filter much smaller. That gave me back a Q of 1.4 million almost, with a loss of 34 dB. And then I tried to load that with 1 megohm, and that dropped the Q from 1.35 to 1.32. And from that I conclude that the impedance is 23 kilo ohm when the crystal has about 10 pF load capacitance. And then I tried to load with 10 pf in parallel with 1 megohm gave me 1.36, and then with only the 10 pf capacitor, and that gave me 1.37, and that is a load put into this schematic. So it means I have these two, that's 10 pf, and then 10 more pf, and with and without that resistor. So it seems more capacitance is favorable. Probably there is a limit when there is a cost again. But before that, I want to look at the power handling of this crystal. I have removed one of the 1 nanofarad capacitors. That loads the crystal significantly, but it gives much more power from the network analyzer. And then I have put an oscilloscope probe in series with a 10 pf from the crystal to the oscilloscope, and then 1 nanofarad from this point to ground. Means the oscilloscope gets 1% of the voltage. Because if I put the oscilloscope directly on the crystal, the Q is destroyed completely. The impedance of the probe is not high enough. It has 10 megohms written on it, but it is more like 1 megohm at 10 megahertz. And here is the frequency response at the power level of minus 30 dBm. And I can check the bandwidth and Q. It says Q is 1.3 million. And I'm sweeping very slowly. Now I increase the power from here to 0 dBm. Now this instrument is defective. I don't know exactly what power it is, but it's the maximum I can get. And here is what it looks like now. You can see the frequency drifts and it follows the signal up, and then suddenly it loses track. This is 100 hertz over the screen, so this power level pushes the frequency away by about 15 hertz. And that might be a reasonable power level for it to operate at, perhaps. The amplitude through the crystal will be kept very constant, so if there is some heating, that shouldn't be a problem. But I want to know at what power level does this happen? And that is what I see here on the oscilloscope. Oops. I think it was something like this. And I have to wait for the maximum. And here it comes again. A little bit more. Something like 96 millivolts. Let's say 100 millivolts. And then there is a factor of 100 in the capacitance ratio. So it means 10 volts. That should be sort of maximum at a load capacitance of, in total, something like 20 pf. So I can estimate this to a power level of 1.7 milliwatts. The total load is that 10 pf loading plus the two 4.7 pf coupling capacitors. So this looks interesting. It would be nice to have 20 of them in parallel, but they are expensive and difficult to get, so that's not possible at all. The crystal is sensitive to temperature, so I will start heating it. And the initial temperature here, 24 degrees. And here is the frequency response. Let's start the heater. And we can see frequency goes up at some reasonably high speed. And I will wait for a while. I can reach 37 degrees. And now it's stable there. I had hoped that the temperature coefficient would be smaller at higher temperature, and therefore that the effect of the frequency drift due to the heating by RF should be smaller. But I don't see any trace of that. This one is more powerful, but it hasn't improved. It seems even to be worse now. If I set the power to -30 here, and look for the bandwidth and Q. It says Q is very low, but that is because the frequency is not stable yet. I think I will wait for a while, but maybe. I don't know really what the temperature is. This thermometer isn't measuring very precisely. But it seems like something like 100 or so. Depending, 130 or something. 200? Well, it's hot anyway. Now it is reasonably stable, and I look for the Q, and it's about 100. Sorry, it's about 1 million. So it is significantly lower now. And that's interesting, but discouraging. But the sensitivity to power is the same. Power and 0 dBm. This is a thermostat oven for the crystal. It's a piece of brass into which the crystal fits well, and then some components glued onto the brass to be a good thermal contact. This is the schematic diagram of the thermostat I made. All the components except for the potentiometer are in very good thermal contact with the brass block. Many enough diodes to make this amplifier happy when feeding it with VCC, which could be 15 volts or something, and ground. So I need to lift the input pin by a couple of volts, 2.5 or something like that. And then I put the potentiometer for the same. And since the potentiometer is just a voltage divider, any temperature drift on that doesn't matter. To investigate the properties of the crystal, now that I have it operating on the proper temperature, about 65 degrees, these two resistors in parallel, and with these approximately 10 pF coupling, presents a 50 ohm impedance on the resonance. And here I have nothing at this time, and this capacitor is in a voltage divider with 2.2 nanofarad. it means that it doesn't load anything on the crystal resistively, or rather the load is extremely small. So I can connect a 50 ohm monitor at this point and look at various effects that I'm interested in. What happens when the power is increased above a certain limit and so forth. This is what it looks like. The thermostat in a temperature insulated box. And no amplifier yet, but this monitor output with the big capacitor to ground. All capacitors are polystyrene. And here is the network analyzer at the power level of minus 30 dBm. And I can look for what it tells me about the Q. It's 122,000. There is a little load from the input, not much, but a little. And the loss of Q is because I have a smaller parallel capacitance to get the correct frequency. Almost. It's a little bit high at the moment. And also because the temperature is elevated. But 1.22 million is not too bad. And the impedance in the feed point input for this filter is 50 ohms with an accuracy that is as good as I can do with this instrument. The resistors form together 56.4 ohms, and 56.4 in parallel with 440 becomes 50 ohms. So, well-known formula tell me 88.7% of the power goes into the resistors and 11.3% goes into the crystal. And I assume nothing goes into the capacitors. I will now do this experiment. The 8657B can be stepped in steps of 1 Hz. I'm using it as a reference frequency close to 10 MHz for these three. They can be stepped only in steps of 10 Hz. But I can put one of them on the center of the filter, vary the power with this stepped attenuator, and then see what happens to the selectivity for the other ones. And I use the Parasus as the analyzing tool. This generator should be for the center frequency of the filter. I have that set to full power, plus 15 dBm. And the attenuators, I cannot see if it's visible, it is anyway 20 decibels. And then I step this generator upwards 1 Hz, and you can see the signal level went down by half a dB. So I go down and then down again, and then down again. So I go up and I note this frequency, that is 11 Hz above 10. And I have calibrated lean rod to show minus 20 dB. That is the 20 dB setting on the attenuator. And I now add a signal 10 Hz up in frequency. And it comes here. And things are slow because I have a narrow bandwidth. Well, I think here. So I read this level minus 40.73. And I used the same generator to look 10 Hz in the other direction. I've set the attenuation to 12 dB now, and I look where is the maximum by stepping this one up and down, looking on the S-meter graph. Now I go down. That was clearly not good. Up, back, and up one more. Yes, that was better. And one more. Not so good. So, at this power level, the offset I need is 12. That is 1 Hz higher in frequency. At 9 dB attenuation, I start to see intermodulation in the crystal. The main signal 10 Hz up and a false signal 10 Hz down. I guess the temperature goes up and down with the beat frequency 10 Hz, and that affects the properties of the crystal. Now the attenuation is 3 dB and the crystal starts to behave irregularly. So I am now at 16 Hz and I step upwards looking at the signal level. 1 Hz, 1 more Hertz, 1 more. Oops. Now it's off resonance and it's not heating anymore. So I go back 1 Hertz. And here I am at the resonance again. And it is now 18 Hertz. Now the frequency is below the resonance by 10 Hertz. That is this signal. And the intermodulation or whatever on the other side is stronger, as you can see. So this level seems to be too high, but I will look at the selectivity curves to decide what is the appropriate power level to run the crystal at, or perhaps the highest possible level that we shouldn't exceed. So these are the measured data and I will plot them on paper. The level of the main signal, here no offset, it's close to the nominal attenuation. That's within better than 0.1 dB. So I will just correct the values I have seen here on the sides with the attenuator setting to get the frequency response curves. I don't see any dramatic things on the selectivity. The center frequency I cannot step finer than 1 Hertz, but the green here, that is 9 dB attenuation, the red is 20, and that is a very small difference. Then 6 decibels, it is blue, it is this one and that one, and no, sorry, black here and here. And 6 decibels could be okay, but 3 decibels, that is more attenuated and less attenuated here, but there is a mirror image which is very strong, and the signal on the other side of the carrier comes here and here, so that is 3 decibels more power. And this is a non-linearity. I don't know what it would mean in an oscillator, but it seems dangerous to run as high as this, as the 3 dB setting. With the 6 dB setting here, the power level I see is plus 3 dBm. So this will be the maximum power I will design for when building an oscillator. With plus 3 dBm input power and 11.3% of the power dissipated in the crystal, the load on the crystal, the power dissipated in it, will be minus 6.5 dBm. I don't know what the datasheet might say, but maybe a bit less than this, I don't know. Into 50 ohms, the signal level is then 9.2 millivolts peak to peak. Well, the oscilloscope is drifting a little bit, but it seems, well, 9.2 millivolts. I have connected the oscilloscope probe across the crystal. And then I'm looking at the monitor output, and I have set the signal level to the same 9.2 millivolts. And of course I need quite a lot of more power to do this, because there are losses in the probe. But I just want to know the voltage ratio between the crystal and the monitor output. So I look here, and what I have on the crystal is 5 volts peak to peak. 5 volts peak to peak on the crystal, that is 1.77 RMS. And I know that the power should be 0.226 milliwatts, because that comes from the computation of the resistors here. 11% of the input power goes to the crystal. And from that I can compute the crystal impedance to be 13.9 kilo ohms. Now I'm looking on the network analyzer again, from the input to the monitor output. Q is 1.22 million and the loss is 37.32. I have placed a 13 kilo ohm resistor in parallel with the crystal. And this is what I see on the network analyzer. This circle here is approximately half the diameter, and the Q is approximately half. It went from 1.22 to 0.68. So I should have used a somewhat smaller resistor, but I haven't done this with the precision motivating such a closer study. And the attenuation has increased from 37.72 to 43.43. That is 0.3 dB from a 6 dB loss. So the impedance is a little bit less than 13 kilo ohms, well in agreement with what I calculated from the not so accurately measured input power. In the next video I will do my best to design an amplifier to put here, which wouldn't load the crystal resistively and which wouldn't have an input capacitance that would detune, at least not too much. Something like 4 or 5 PF is too much, because it wouldn't be in resonance anymore. And with very low noise.